Could we really deflect an asteroid heading for our Earth? Experts explains NASA's latest DART asteroid mission. Now, we've had an asteroid 66 million years ago putting an end to the dinosaurs. We have scars on Earth. This is the Manicouagan crater in Canada and other craters across the United States, the Barringer crater. And this is only a 10-year map showing the volley of events, small asteroids. The yellow is daytime and the blue is nighttime. So this is only a 10-year map. You can see where they've landed. It looks like to me, I may be blind, but it looks like to me most of them are nighttime. And of course the asteroid belt, you can see between Mars and Jupiter. That's where most of the asteroids lie. But we do have bigger asteroids coming to us from the direction of Jupiter. So what can we do about these? Could we really deflect an asteroid coming towards us in order to protect Earth from Earth impact? Gail Illis from The Conversation reports, a NASA spacecraft size of a golf cart has been directed to smash into an asteroid with the intention of knocking it slightly off its trajectory. The test aims to demonstrate our technological readiness in case an actual asteroid threat is detected in the future. That's assuming that we'll be able to get a spacecraft up there to do the same thing. Now, the Double Asteroid Redirect Test, DART for short, lifted off aboard a SpaceX rocket from California November 23rd. It will arrive at the target asteroid system in September of next year. The mission will travel to the asteroid Didymos, meaning twin in Greek, a member of the Amur group of asteroids. Every 12 hours, Didymos is orbited by its mini-moon or moonlet called Dimorphos. This smaller half of the pair will be the target for DART mission. Are we facing an extinction threat from asteroids? We've all seen disaster movies in which an asteroid hits Earth, creating an extinction event similar to the one that killed off the dinosaurs 66 million years ago. Could that happen now? Well, Earth is actually bombarded frequently by small asteroids ranging from 1 to 20 meters, 20 meters being about 60 feet in diameter. And most all asteroids of this size disintegrate in the atmosphere and are usually harmless. There's an inverse relationship, though, between the size of these objects and the frequency of impact events. This means we get hit much more frequently by smaller objects than larger ones, simply because there are many more smaller objects in space. Asteroids with a 1 kilometer diameter strike Earth every 500,000 years on average. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. The most recent impact of this size is thought to have formed the Tenumur impact crater in Mauritania 20,000 years ago. Asteroids with an approximate 5 kilometer diameter impact Earth about once every 20 million years. 5 kilometers, of course, is huge. That's 3 miles. So that is a huge piece of rock. The 2013 Chelyabinsk meteoroid, which we did not see coming into us, which damaged buildings at 6 Russian cities and injured around 1,500 people, was estimated to be about 60 feet in diameter, 20 meters. Now, assessing the risk, NASA's DART mission has been sparked by the threat and fear of major asteroid hitting Earth in the future. The Torino scale is a method for categorizing the impact hazards associated with near-Earth objects, NEOs. It uses a scale from 0 to 10, wherein 0 means there is negligibly small chance of collision, and 10 means imminent collision, with the impacting object being large enough to precipitate a global disaster, meaning an extinction level event. The Chicxulub Yucatan impact was of 66 million years ago that did away with the dinosaurs, was at the Torino scale of 10. The impacts that created the Barringer crater and the 1908 Tunguska event both correspond to Torino scale of 8. With the increase of online news and individuals' ability to film events asteroids near misses tend to generate fear in the public. Currently, NASA is keeping a close eye on asteroid Bennu, which is the object with the largest cumulative hazard rating right now. With a 500-meter diameter, that's 1,500 feet, Bennu is capable of creating a 3-mile crater on Earth. 3 miles, 5 kilometers. However, NASA has also said there's a 99.943% chance the asteroid will miss us and will not impact us. So we have to brace for impact. At one point in their orbit around the Sun, Didymus and Dimorphos of the DART mission will come within about 5.9 million kilometers of Earth. That's about over 3 million miles. This is still further away than our moon, but it's very close in astronomical terms. So this is when DART will hit Dimorphos. DART will spend about 10 months traveling towards Didymus, and when it's close by, it will change direction slightly to crash into Dimorphos at a speed of about 6.6 kilometers per second. The larger Didymus is 780 meters in diameter and thus makes a better target for DART to aim for. Once DART has detected the much smaller Dimorphos moonlet, just 160 meters in diameter, that's 500 feet, it can make a last-minute course correction to collide with the moonlet. The mass of Dimorphos is 4.8 million tons, and the mass of DART to impact will be at 550 kilograms. So will it nudge it? We're talking about 5 million tons as opposed to 550 kilograms. Sorry about that. So I don't know. Now, traveling at 6.6 kilometers per second, DART will be able to transfer a huge amount of momentum to Dimorphos to the point where it's expected to actually change the moonlet's orbit around around Didymus. The question is, what happens if it doesn't change? Now, this change, the scientists say, to the tune of about 1%, will be detected by ground telescopes within weeks or months. While this may not seem like a lot, 1% is actually a promising shift. If DART were to slam into the lone asteroid, its orbital period around the Sun would change by only about 0.000006%, which would take many years to measure. So we'll be able to detect the 1% change from Earth, and meanwhile the pair will continue along its orbit around the Sun. DART will also deploy a small satellite 10 days before impact to capture everything. This is NASA's first mission dedicated to demonstrating a planetary defense technique. At a cost of about $330 million in the US, it's relatively cheap in space mission terms. The James Webb Telescope, which launched a few days ago, costing $10 billion. There will be little to no debris from DART's impact. We can think of it in terms of comparable event on Earth. Imagine a train parked on the tracks, but with no brakes on. Another train comes along and collides with it. The train won't break apart or destroy one another, but will move off together. The stationary one will gain some speed, and the one impacting it will lose some speed. The trains combine to become a new system with different speeds than before. So we won't experience any impact, ripples, or debris from this DART mission. Is the effect really worth it? Results from the mission will tell us just how much mass and speed is needed to hit an asteroid that may pose a threat in the future. We already track the vast majority of asteroids that come close to Earth, so we would have early warning of any such object. That said, we have missed objects in the past. In October 2021, asteroid UA1 passed about 3,047 kilometers from Earth's surface over Antarctica. We missed it because it approached from the direction of the Sun. You see, this is what the big space agencies can't do. They cannot dip their telescopes towards the direction of the Sun low enough to see what's coming from the direction of the Sun. It's only these amateur astronomers, the ones that have recently found the two interstellar comets, that have found them because their telescopes were aimed at the direction of the Sun. So that's not a good thing for us. So if a lot of them do come from the direction of the Sun, we won't see them with our space agencies, unless some amateur astronomer finds them first. Now, at just 1 meter in size, 3 feet in size, it would not have caused much damage, but we should have seen it coming. This we're talking about the asteroid UA1 that passed over Antarctica, October 2021. Building a deflection system for a potential major asteroid threat would be difficult. We would have to act quickly and hit the target with very good aim. One candidate for such a system could be the new technology developed by the US spaceflight company Spin Launch, which has designed technology to launch satellites into orbit at rapid speeds. This device could also be used to fire masses at close passing asteroids. We'll see what happens. This is from the conversation on phys.org. Please leave your comments and thank you for your support.